In this video we're going to look at different types of power amplifiers called push-pulls. Push-pulls are very good amplifiers, and they're the most popular linear power amplifiers in use today. Our Class B amplifier had a conduction angle of pi, which meant that we had really bad distortion at the output. It had sort of a weird shape that looked like half a bump instead of a sine wave. One fix for that issue is to make a Class B push-pull stage, which is pictured on the left. This looks like two emitter followers, one NPN up here and one PNP down here, that are stacked on top of each other. Push-pulls are set to have Q1 conduct for pi radians while sourcing current to RL, and Q2 to conduct for pi radians while sinking current from RL, so we drive current either down through Q1 or back down Q2. The axes for a transfer characteristic are set up in the upper right. We can start filling in that transfer characteristic by noting that when Vin is close to 0, neither Q1 nor Q2 is turned on. So Vout doesn't change when Vin does. That behavior is called a dead zone or a dead band. And it ends when Vin reaches either negative VB on to turn on Q2 or positive VBE on to turn on Q1. Once Q1 or Q2 turns on, that device acts like an emitter follower until it saturates, just like Class A amplifiers. Reaching those saturation points is unusual because VCC minus VCE sat is quite high value and requires our input to go to VCE minus VCE sat plus VBE on. One side note, if you need to do small signal analysis for some reason, maybe estimating the peak output resistance or something, you can just treat the circuit as an emitter follower in either of these zones, because one device is going to be conducting, say over here Q1 is conducting, while the other one is cut off, so this doesn't take any current. So this just looks like Q1 loaded by RL connecting the emitter to ground. So this is a weird voltage transfer characteristic because of the dead zone, and that shows up in our output sine wave. So specifically our Vout voltage is going to stop changing for little stretches whenever our input signal crosses 0, and that behavior is called crossover distortion. That's bad, but you might not care if your input signal is sufficiently large because it'll become a small fraction of your signal. And we can see here that it's Q1 and Q2 both have conduction angles of about pi, Q1 during this positive half cycle and Q2 during this negative half cycle, which is why this is called a Class B push-pull. One final note, this is convenient design because the biasing is really easy. We don't actually have to do any, other than making sure that Vn is in the right spot. It's common to try to fix crossover distortion using a topology called a Class AB push-pull, and I've drawn one of those on the left. The big idea in a Class AB push-pull is that the on voltage of this diode cancels out the VBE on of the conducting device. So, for example, if this base node has a voltage of 0, then this node will have a voltage of V on, which means that Q1 will respond immediately as our input node starts to increase above 0. That gives rise to the voltage transfer characteristic I've drawn on the right over here. There are a few details to note about this plot. First, kind of beating a dead horse, reaching this Q2 saturation point, or this Q1 saturation point, presumes all of our internal nodes behave well. So specifically it presumes that this node will be able to fly past VCC, and that requires that this current source behave unusually well, or that we power everything from a rail higher than VCC. So typically our swing in this amplifier is limited by our driver to this linear range. Second, there's a narrow window in the middle of this amplifier where both Q1 and Q2 are conducting. By definition, that means that both Q1 and Q2 have conduction angles that are greater than pi, which is why this is called a class AB amplifier. It's partway between the 2 pi conduction angle of class A and the pi conduction angle of class B. It also means that we're susceptible to a cool circuit failure mode called thermal runaway. Thermal runaway comes from the fact that VBE on is dependent on temperature. So if there's a slight mismatch in these diode voltages, such that, say, this one's bigger, then in this region, Q1 will be more conductive than Q2, and it will take more of the current being driven into RL. That'll make Q1 hotter than Q2, which shrinks its VBE on further, so it takes even more current. And you get this positive feedback process where eventually the hotter transistor takes all the current and lights itself on fire. Fortunately, you can avoid thermal runaway by adding a little bit of degeneration resistance. If you add a little resistor on the emitter of Q1 and Q2, and in series with both of these diodes, you basically fix thermal runaway problems. Class B and AB push-pulls have better efficiency than Class A amplifiers, and we're going to show that in a derivation here. Like the other efficiency analysis, we're mostly interested in the results and a chance to see the process. And this analysis is for Class AB amplifiers, but it's pretty accurate for Class B amplifiers too. As test conditions, we set our large signal Vin to 0, so we don't get any DC current in RL. And we set our little Vin to VCC minus VCE sat, our maximum swing times sine omega t. Again, we're going to find out that this maximum swing is when our amplifier is most efficient. We'll pull that out of our results at the end of the derivation. I want to pause for a moment to note that if everything is working right in this amplifier, then our output voltage is equal to our input voltage. This node is Vin. It jumps up to Vin plus V on here, and then falls back down to Vin plus V on minus VBE on. And if we're doing a good job, then V on and VBE on cancel each other out, so that V out is equal to V in. We're going to care how much current is drawn from the supply, so I'm going to start by calculating that separately here. We need to average our current, which is given by V out over RL. And we're going to do so by averaging that signal, that V out over RL signal, over the period of time that Q1 is conducting, so across its conduction angle of pi. And we're doing this integral with respect to omega t, which allows us to use the conduction angle for the limits of the integral. And because we're taking an average, we divide by the period we're averaging over, so we get 1 over pi out here. So this is just a written out expression of the time average of the current coming from the supply, V out over RL. Integrating, if we subbed this expression in here, we find that we're mostly integrating sine omega t over pi, which is equal to 1. So the current, the time average current that comes out of VCC is VCC minus VCE sat over pi RL. The power pulled from the supply is the power pulled from VCC plus the power sunk into minus VCC. And I've written that out here. The power pulled from VCC is VCC times this time average current. And the power sunk into minus VCC is an exact symmetrical process where we have current going into minus VCC through Q2 during the half cycle from pi to 2 pi. So we can write this as 2 VCC times the time average IVCC, and overall that comes out to this expression. Finding the power in the load is a little bit easier because our load's a resistor, so it's just going to be V out squared over RL. And V out squared has a sine squared in it, so time averaging that turns into a factor of 1/2. Finally, we find the efficiency by taking the ratio of the average load power to the average source power. This comes out to pi over 4 times VCC minus VCE sat all over VCC. If VCE sat is small, this result is about 78%, which is more than 3 times better than our Class A amplifier. We also back off more gracefully because IVCC scales with our V-in amplitude. However, IVCC is all right. This expression here is just our maximum input amplitude. If we put in a smaller one, IVCC would be smaller. However, our IVCC is always pulled from a full 2 VCC here, so we still pay a penalty if we're not driving our signal at its maximum amplitude. So in summary, push-pulls use 2 devices, one to source current for about half the cycle and one to sink current for the other half. Class B push-pulls have crossover distortion. Class AB push-pulls use diodes to cancel out crossover distortion, but they have a risk of thermal runaway, which we fix with degeneration resistors. And Class B and Class AB amplifiers achieve a peak efficiency of about 78%, with pretty good back-off.